Last time we discussed the equation of state relating pressure, density, and temperature, and now to continue with thermodynamics, we'll be continuing with what I call the thermodynamics relationship, um, which just to give some spoilers, is this equation right here. It's basically telling how density changes is related to how how a logarithm of specific volume or density is related to the logarithm change of temperature minus the differential of the logarithm of pressure. So first things first is to define a specific volume, which is the inverse of density. So density is the mass per volume is equal to density. Well, 1 over density, alpha, is equal to the volume per mass. So it's basically saying if you have a unit of mass, how much volume of the substance itself would be there. And we know that density, as well, and obviously as well as specific volume alpha, because they're, you can just flip them, they are both a function of only temperature and pressure. And so we know from partial differentiation that we can find the differential of the logarithm of specific volume is equal to partial ln alpha divided by partial t, holding p constant, times the differential of temperature, plus partial ln alpha partial pressure holding temperature constant dp. And if we were to do this for some variable that happened to be a function of more than just temperature and pressure, which I personally think could be possible if we're dealing with maybe water inside of another gas, such as air, how that would affect the density of the air itself could have an effect, for example. But usually it's accepted that temperature and pressure are the only variables that the rho depends on. And if, for example, it had 3 or more, it would look something like this. We'd, if alpha was a function of a, b, c, etc., we'd take the derivative in terms of a, holding all other variables constant, so b, c, etc., dA, and then the next one would be d partial alpha partial b, holding a, c, dot dot dot, constant, and then dB. But in our case, we're just going to use this equation. And now using the equation of state, if we assume that this equation is actually, universally true, and I don't think anyone has found a better equation for this, we usually tend to assume this is true. Now, this is making some big assumptions. One is that the air molecules, as they're moving around, that they're not exerting external forces on the other air particles, and that rather we have a bunch of air particles that have space between them and they're just colliding like these billiard balls. So I'm not 100% sure how accurate that is, but this has been tested in laboratory and has been pretty accurate most of the time, and except maybe in extreme circumstances. And I'm assuming that it's likely some sort of linear regression that's being done to determine this to be true, as I'm sure there's some sort of error in this. But for the most part, this is pretty accurate. So now using this, we can apply the rules of logarithm to this equation. So, for example, if we take ln of a times b, that would be equal to ln of a plus ln of b. And then ln of a over b, for example, would be equal to ln a minus ln b. And so we can do that in this case. We take this equation, we divide by p on both sides. We get alpha is equal to r dt over p. And taking ln alpha, we get the multiplication of the top part gets you ln t plus ln rd minus the bottom, which is ln p. And so that's what we have here. Now we can try to solve for these two terms that were in this expansion up here. The first one is called the coefficient of isobaric expansion. Isobaric means same, iso, and baric is pressure, so held at constant pressure. And the coefficient of isothermal expansion is how where temperature is held constant, thus isothermal. And to solve for these two terms, we can take this equation we've just done here and we can differentiate this one. So if we differentiate in terms of temperature, holding pressure constant, we can get rid of this term because the derivative of a constant is 0, same for this term. And we're left with partial ln t, partial t, which from calculus is just 1 over t. And then similarly for partial ln alpha, partial p, holding t constant, we get rid of the last two terms, and we're left with negative partial ln p, partial p, which is equal to negative 1 over p. Now, plugging these back into the equation, here and here, we will come up with that d ln alpha is equal to 1 over t dt minus 1 over p dp. Now we can apply a form of the chain rule, which I, before being in this field, I did not really come across this before. So I think it's very specific to more applied fields such as geophysics. It's very common to write things in terms of logarithms because they kind of clean up the algebra. So if we take the derivative of a function, for example, df of g, where g is an inner function inside of the function f, then we can, that will be equated to df of g dt times dg dt. So in the case of ln f, we get d ln f is equal to 1 over f, because derivative of ln f is 1 over f, times df. And so these two terms, we would get d ln t, and this term here, we would get d ln p, and that gives us our thermodynamic relationship, as I call it. So that's going to be the d ln alpha is equal to d ln t minus d ln p. It basically says if there's any increase over any metric, such as time, for example, that it's equal to the change in log temperature minus the change in log pressure. And we could, for example, differentiate this over time, dt, to give us an equation called the temperature tendency equation, which basically tells you, if you know temperature, and you know the change in pressure over time and the change in density over time, then you know the change in temperature over time. And if you're curious how we got rho back in here, what we basically did is we said d ln alpha is equal to d ln rho to the negative 1 by definition, and you can take the negative out. That will give you negative d ln rho. And so this term is gets added, so it's positive, and this term will be now a negative term as we just wrote here, and that will give us this equation here. So we could also write this equation, we could change this term, it would be plus t d ln alpha dt. But this is more standard because specific volume is more of used to simplify the derivation, but when doing calculations we tend to deal with density, as I believe it's easier to calculate. And another thing we we should notice is, let me make a quick correction to that, is if we're dealing with an incompressible fluid such as water, while air is a compressible fluid, meaning you could, put it, if you put it into a glass and you put a piston, push it inside of there, you'd still be able to close the whole thing. While if you're dealing with water, it cannot be compressed, so it will try to find a way out. And in the case of a compressible fluid, we can make an assumption that the specific volume is only a function of temperature and not of pressure, because of that incompressibility is related to pressure. There's no dependence on that, except in maybe extreme situations. You might have really high temperature that might eventually bring out the compressibility of water, which will then have to include pressure, but that's so rare and doesn't really affect the system itself, so you can ignore it. And in that case, we would only be left with the term taking the derivative in terms of temperature, because taking the derivative in terms of pressure would result in 0. And so that's nice to note. Now, next we are going to be looking at the thermodynamics equation, which is an equation where most of the variables within that equation we have already solved experimentally for their values. And just as a sneak peek, it's Cp times dt d time minus alpha dp dt is equal to dq, which is heat dt. And so we know the value of Cp, and we can focus on this heating term, which in atmospheric science, a lot of things can affect this term, such as convection, cloud formation, evaporation, precipitation. All those kinds of processes affect the heat of the system. The sunlight, solar radiation, is one thing. So this equation tends to be used over the previous temperature tendency equation that we just learned. And so we will discuss that in the next video. Stay tuned.